Hey folks, let's finish up our notes here on particle motion. So sometimes we aren't given an equation or a graph, but rather a table. And that's one of the big ideas of AP Calculus, is that you can handle any situation in three different forms. You could be given the equation, you could be given the graph, or you could be given a table. And so if you look at the last couple of notes that we did, here was a situation where we were given the graph. Here was a situation where we were given an equation. And now we're doing the third form of information that's given in a table. In these cases, we're at the mercy of the limited information given to us. So we can't really say a lot about what the function is. We don't know if it's a polynomial. We don't know how it behaves beyond the points that they've given us and what they've told us in the story. Sometimes, too, we are not given units. Yay, whenever this happens, life is good, because that means this liberates us from having to include them in our answers. Okay, so let's get after it. The values of the coordinate S of a bug moving smoothly and continuously along a line for various values of t as an element of 0 to 4 inclusive are given below. So as always, the best skill in this class is the ability to annotate and the way they say it and what it means. If my function is moving continuously, well, that means that my function is continuous. Now, on the other ones, we didn't really need to worry about that, because when I'm given a graph, I can just look to see if it's continuous. And if I'm given an equation, I can look at the family of functions that it belongs to and understand whether or not there's any continuity. This phrase of being smooth means that we are differentiable. That means that we are everywhere differentiable if our bug moves smoothly. That means that there aren't any sharp turns like there is in the absolute value function. All right, so we now know that our movement of our bug is differentiable and continuous, and we know that our time period is from 0 to 4. What's nice is it's not in seconds, so we don't need to worry about writing that part out. Okay, so what is the displacement of the bug during the given interval from 0 to 4? Show the work that leads to your answer. I'm going to encourage you to pause here and see how much you can do on your own of this one. All right, so hopefully you annotated. Even if you knew what this word meant, I still recommend annotating. Displacement means take the end and subtract the beginning. So displacement can be negative. All right, so what's the end of our interval is at time 4. What's the beginning of our interval? That's at time 0. So we would want to figure out what's the position at time 4. S stands for position. So what is our position at 4? Whatever's for time units. Minus what is our position at 0 time units? We'd go ahead and start to look up here. S of 4 would be 0.2. S of 0 would be 40. Subtract those, and we end up with negative 39.8. Now, they didn't have any units, so we don't have to worry about that. Also, we didn't have any explain or justify, so they just said show the work, so this is good. Now, if we did have to do any of that, what is something that we could say? Pause and try to say what this means. Okay, what this means is that my particle moved 39.8 units to the left between the 0 and 4 seconds. Overall, that's what happened. In between, I don't know what happened. I don't know what happened to my particle going back and forth. But I do know overall, it ended up 39.8 units to the left of where it started. What is the minimum number of times the bug changes direction from 0 to 4? All right, here we go again. I want to highlight, I want to annotate. Changes direction. Okay, when does a bug change direction? I'll give you 5 seconds. When does anything change direction? How do we know when something changes direction? That's a better way to say it. Because velocity switched signs. That's the only way I can guarantee that my function, or sorry, that my particle, in this case a bug, changed directions. Anything else would just be kind of wordplay. It wouldn't be a way to prove that it happened. Okay, so I'm going to go up here and I want to make a little sketch of what's happening to this bug. Now, our bug starts 40 units away from 0. So this is 40. I'm going to put 0 in here as a reference. So what does our bug do first? Our bug goes from 40 to 35 to 30 to 36. So I can think, as I think about this, my bug went from 40 to 30. And then somehow, at some point, I don't know if it was exactly at here, but then it went back to 36. Then it went to 48. So then my bug goes all the way to, I wish I'd have done a better job of this, 48. Then what does my bug do? Then it goes from 48 to 45 to 30 to 16 to 2. So the 0.2, I should say. And it goes all the way basically back down to 0. So from this chart, our particle, or our bug, we could say our bug has changed directions twice. It went left, it went right, then it went left again. But that's not a good enough reason. That's not a good, because I drew this chart, well, we don't know when does it turn around. So what we're going to do is we're going to try to come up and try to figure out some values of velocity. So remember, we can get a decent estimate of velocity by doing the slope. So a pretty good estimate of velocity from time equals 0 to, okay, when do we think our particle first changes direction? It goes from 40 down to 30, and then it goes up to 36. So I think it changes direction somewhere in here. Or somewhere in here, I guess I could say. But for velocity from t equals 0 to t equals 1, let's say. So let's figure out what that velocity would be. Velocity would be, I would figure out my velocity at, so velocity is a change in position divided by a change in time. So what is our position change? Well, at time 1, we're at 30.2. Minus at time 0, we're at 40. And we went from 1 minus 0. This ends up being, I don't actually care what the number is. I just care what its sign is. 30 minus 40 is negative. A negative divided 1 minus 0 is a positive. A negative divided by a positive is negative. So my velocity from 0 to 1 was negative. Now I'm going to calculate my velocity from 1 until my velocity from t equals 1 until, when do I think we change back? I think at round 2, we change back to the other direction. So I'm going to look at what happens from time 1 until time 2. So my velocity equals, again, change in position over change in time. So my position at times 2 is 48.2. At 1 is 30.2 over 2 minus 1. And again, because I'm talking about changing direction, I don't care what the actual velocity is. All I'm trying to do is compare the signs of velocity. So 48.2 minus 30.2 is something positive. 2 minus 1 is positive. A positive divided by a positive is positive. So I've guaranteed that my particle, my bug, I keep getting it mixed up, my bug changes directions at least one time because my velocity switched signs at one time. Now, do I know where it switched signs? No, I don't know. I don't know. But I do know that it switched somewhere. Okay, so let's do this again. Let's see. We know that there's another time. The velocity from time equals 2 until, and then it goes all the way until 4. So my velocity is the change in position over the change in time. At 4, it is 0.2. At 2, it is 48.2 over 4 minus 2. 0.2 minus 48.2, that's a negative. 4 minus 2 is a positive. A negative divided by a positive is a negative. Now, let me just go back. Notice in the annotating, in the sentence, they said, what is the minimum number of times? Why do we only care about the minimum number of times? Well, because the maximum, this thing could have changed directions infinitely many times. We don't know how. It could have changed directions a bunch in between 40 and 35. We don't have enough information. But because we do know that the velocity switched signs twice, that we know that at least it had to have happened twice. The minimum, we say minimum because it could happen infinitely many times. Okay, so let's do a little write-up here. So what do we want to say? So we want to say something like the bug changes direction at least 2 times because, what's our argument why? The bug changes direction at least 2 times because velocity switches signs at least twice. What is the bug's average velocity from time equals 0 to 0.5? Show the work that leads to your answer. So nice, no justify. I'm going to leave this one up to you. You guys should be able to do this. Pause it if you haven't yet. Okay, let's see how you did. Annotate. Average velocity. That word average is a huge clue. That means it's going to be the slope of, okay, if I want to figure out the average velocity, that's the change in that's the average velocity is the change in position over time. So that's the slope of position. 2 points. We have 2 points of position. So average, we usually write V average, velocity average, is the change in position. So that's my position at 0.5. Subtract my position at 0 over the change in time. So our position at 0.5 was 35. I'm just looking at the chart up above. My position at 0 was 40 over 0.5 minus 0, which is 35. That's negative 5 over 0.5. And you would be expected to do this without a calculator, so there's 2 ways to do it. Dividing by a half, flip and multiply, times by 2. Or you could move the decimal point over for each of them, make this a 50, and make this a 5. Either way, negative 50 divided by 5 is negative 10. I don't need units, and I don't need a justification, because it doesn't say I have to. But if there were a justification, I would say something like, on average, the particle's velocity was negative 10 for all time t. That's an element of 0 to 0.5. Or I could say that my particle's position was decreasing by 10 for all times t is an element of 0 to 0.5. All right, now here's a new word. This is something we haven't talked about yet. This is that word estimate. The word estimate is a huge indicator. This means that your answer is going to have approximately symbols. This is the only time we use approximately, is when you see the word estimate. So we're making an estimate of the particle's velocity. Now, if I just say the particle's velocity, is that an AROC or an IROC? Since they just said velocity, This is an IROC. They didn't say average. They have to say average. So when they don't say average, they mean instantaneous rate of change. Okay, so here's the problem. Here's the problem. We don't have an equation. We don't have a graph that we can look at to figure out what the instantaneous rate of change is. That's why they call it an estimate. So there are three ways in which you can use a table to figure out an instantaneous rate of change. So option one, we're going to call this option one. If I want to figure out the instantaneous rate of change at 0.5, what I can do is I can go up to 0.5 and I can pick the two values around 0.5 and figure out their slope. The slope between 0 and 1 will be a pretty good estimate, probably. We don't have enough information here, but it's the best we can do based on this. To find the slope here, what we're going to do is find the slope of the things around it. That's one option. So I would say V of 0.5. Notice, approximately, because we don't have a good way, we don't have a really good answer to this. The best we can do is approximate it. So that's position 1, subtract position 0 over 1 minus 0. Then this turns into an equal sign as you keep going. It's really weird. So this is an estimate of velocity, but this value does equal 30.2 subtract 40 over 1 minus 0. So what I used to do as a teacher, even, when I would put approximately, I would write approximately all the way to my answer, and that's actually incorrect. Because this is approximately equal to this, but this is equal to this, because all we did was plug in those numbers. So you should change this approximately to an equal sign as you go through. I know it's confusing, but that's the way we write it up. So 30.2 take away 40 is negative 9.8 over 1 is negative 9.8. That is our estimate for the velocity at the instantaneous velocity at time equals 0.5. So notice when we make an estimate, I'm just going to highlight this again. We start off with an approximately, but as we continue through our calculation, it changes to an equal sign as we go through. All right, so the other two options to figuring out an estimate for an instantaneous velocity from a table, you can do, the other options are to take this and do their slope, or you could do this and this to do the slope. So for me to get a velocity at 0.5, I can use the points around it, or I can use 0.5 with the point before it, or I could use 0.5 with the point after it. So it doesn't matter. Either one of those are fine. So let's go with option 2 for the other one. So option 2, we want to figure out what's happening at 2.7. So I go up to my chart at 2.7. Now what I could do is I could do the slope between 2 and 3. That would give me a pretty good estimate of this. But I want to try one of these other options. This is what we call option 2. My velocity at 2.7 is approximately, because we can't get a good estimate here, or sorry, we can't get an exact value here, so we want to use an estimate. Now, I could, at 2.7, I could use this or this. Either one of those are fine. I'm going to use the first one, let's say. Okay, so that would be that would be S of 2.7, subtract S of 2, darn it, that's 0, S of 2 over 2.7 subtract 2. Now, as I continue on, this thing is going to be equal to, when I plug in the values for these, at 2.7 I get 45.0. At 2 I get 48.2 over 2.7 subtract 2. Oh boy, this would be negative 3.2. I'm not going to clean this up. So this would be, well, 45 minus 48. I got like negative 6.8, but that's way off. Where did I get that from? Huh. This would be what? Negative 3.2 over 2.7 take away 2. Am I looking at that right? Yeah, I'm looking at that right. Huh. Oh, I bet you I used this one in my notes from before. Sorry. 2.7 minus 2 is 2.7 minus 2 is 0.7. I don't want to clean that up, so this is a free response, so I can just stop there. If I had a calculator, maybe I would type it in, whatever. So option 1 is depict the things around it. Option 2, actually, I'm going to scribble this out and just call this option 1. And then I'm going to say this, either one of these are option 2. I don't like the way I wrote that. Option 1, option 2. Now this one is not going to be, your hands are tied with this one. Give me an estimate of the velocity at 3.5. I look up at 3.5 and there is no 3.5 in my table. So my hands are tied here. I have to use these two. So I'm going to find the gap between those two. I'm going to do a different color here. Okay, so this is not really an option. This is the only way I could do it because there isn't a 3.5 to work from. They said estimate, so I need to have an approximately symbol. My position at 3.6. Take away my position at 3. At 3.6 is 16. At 3 is 38.2. Another one that's not going to be fun. Oh, gosh darn it. Never mind. This should say 33.6. Take away 3. Then this is 16. Take away 38.2 over 3.6. Take away 3. Which equals, what's that, 16 plus another 6.2, so negative 22.2 over 0.6. I'm going to double check that with my calc, which is probably cheating, but I want to make sure that it's right. Yeah, negative 22.2. Okay. So, from the information given, is it possible to determine the time and position of the bug when it's farthest away from the origin? No, we can't say that. Nope. Why or why not? Well, let's just talk through it. How do I know that the particle right now, what's the farthest from the table, what's the farthest the particle is away from the origin? Well, right now, the best we can say is that it's 48.2. But what if in here it's at 48.3? We don't know if it continues to go farther to the right, then it starts to go to the left. We know eventually it starts going to the left, but we don't know when. So from a table, unfortunately, we're not able to exactly find that value. All right, folks, so that's it for notes here in 2.5. Hopefully you've already been doing some of the homework, but let's get after it.